All right, the mysterious wave-particle duality continued, and quantum mechanics, the wave equations as they're known as. Yeah, so a summary of recent material we've done. Of course, we've got the interference patterns of a single interference pattern that a lot of people ignore. Yeah, people often look at this part and say there's no interference pattern, but there certainly is. So photons coming through one by one still do this. They land in certain spots and build up this pattern over time. Versus the double slit interference pattern, right? Spots where photons would have arrived, but now they don't when you open that extra slit. Very odd stuff, right? So yeah, do other particles do this is the question, right? We see photons as particles doing this, and so we're wondering if other particles do this, and the answer is yes. Electrons firing through slits do this. This isn't what you'd get. You wouldn't just get two spots behind the open doors here. You'd actually get an interference pattern, as it turns out. So here we go. In the first few decades of the 20th century, many of the greatest theoretical physicists grappled tirelessly to develop a mathematically sound and physically sensible understanding of these hitherto hidden microscopic features of reality. In other words, that particles and waves, right? Particles of light have to be true, but it also has to have wave properties. Under the leadership of Niels Bohr in Copenhagen, for example, substantial progress was made in explaining the properties of light emitted by glowing hot hydrogen atoms. But this and other work prior to the mid-1920s was more a makeshift union of 19th century ideas with newfound quantum concepts, rather than a coherent framework for understanding the physical universe. Not really explaining anything, right? It was just good at calculating things and getting right answers. Compared with the clear and logical framework of Newton's laws of motion or Maxwell's electromagnetic theory, the partially developed quantum theory was in a chaotic state. In 1923, the young French nobleman Prince Louis de Broglie added a new element to the quantum fray, one that would shortly help to usher in the mathematical framework of modern quantum mechanics, and that earned him a 1929 Nobel Prize in Physics. Inspired by a chain of reasoning rooted in Einstein's special relativity, de Broglie suggested that a wave-particle duality applied not only to light, but to matter as well. He reasoned, roughly speaking, that Einstein's E equals mc squared relates mass to energy. Relates mass to energy. It's not the same sentence. Well, that Planck and Einstein about, yeah, actually it is. That I'm just not enunciating it properly, I guess. The Planck and Einstein had already related to energy and frequency of waves, and therefore by combining the two, mass should have a wave-like incarnation as well, right? So E equals mc squared was used to relate matter and rate energy to frequency of waves, and so mass should have a wave-like counterpart as well. After carefully working through this line of thought, he suggested that just as light is a wave phenomenon, that quantum theory shows to have an equally valid particle description, an electron, which we normally think of as being a particle, might have an equally valid description in terms of waves. Einstein immediately took to de Broglie's idea as it was a natural outgrowth from his own contributions of relativity and of photons. Even so, nothing is a substitute for experimental proof. Such proof was soon to come from the work of Clinton Davison and Lester Germer. In the mid-1920s, Davison and Germer, as it's called, experimental physicists at Bell Telephone Company, were studying how a beam of electrons bounces off a chunk of nickel. Remember the nickel crystal stuff, right? The only detail that matters for us is that nickel crystals in such an experiment act very much like two slits or multiple slits, as illustrated in the figures in the last section. In fact, it's perfectly okay to think of this experiment as being the same one illustrated there. Same as the one, whatever, except that a beam of electrons was used in place of a beam of light. We'll adopt this point of view when Davison and Germer examined electrons making it through the two slits in the barrier by allowing them to hit a phosphorescent screen that recorded the location and impact of each electron by a bright dot. Essentially what happens inside of a television. They found something remarkable. Old school television, right? Cathode ray tubes. I think I mentioned those before in the electromagnetism unit. A pattern much akin to exactly the same, really, as figure 4.8, the interference pattern, right, emerged. Their experiment therefore showed that electrons exhibit interference phenomenon, a telltale sign of waves. At dark spots on the phosphorescent screen, electrons were somehow canceling each other out, just like the overlapping peaks and troughs of water waves. Even if the beam of fired electrons was thinned so that For instance, only one electron was emitted every 10 seconds or 10 hours. The individual electrons still built up in bright and dark bands, one spot at a time. Somehow, as with photons, individual electrons interfere with themselves in the sense that individual electrons over time reconstruct the interference pattern associated with waves. We are inescapably forced to conclude that each electron embodies a wave-like character in conjunction with its more familiar depiction as a particle. Although we have described this in the case of electrons, similar experiments led to the conclusion that all matter has wave-like character. But how does this jibe with our real experience of matter as being solid and sturdy, in no way wave-like? Well, de Broglie set down a formula for the wavelength of matter waves, and it shows that the wavelength is proportional to Planck's constant. More precisely, wavelength is given by Planck's constant divided by the material's body's momentum. Since h bar is so small, the resulting wavelengths are similarly minuscule compared to everyday scales. This is why the wave-like character of matter becomes directly apparent only upon careful microscopic investigation. Just as the large value of c, the speed of light, obscures much of the true nature of space and time that we'll learn about soon in the next unit, the smallness of h bar obscures the wave-like aspects of matter in our day-to-day life, right? So we've got that same equation as we saw for the momentum of light. Since we have this number being so small, yeah, very, very hard to notice. So yeah, quote unquote real particles, if we're not yet considering particles of light as being real, that's why it's in quotes. They are real though. But yeah, as I showed already in the previous video, electrons and neutrons and even helium nuclei, can go through two slits and arrive as particles and arrive as a wave, right? So not only is light both a wave and a particle, but particles are both, particles and waves as well, right? In other words, both of them have particle and wave properties. There's a wave-particle duality, so to speak, as they say, right? So again, looking at so-called real particles through two slits, this little video section from 1245 to 1505. I better jot that down. I'll get this ready.
Fuck out from under that.
One test in particular, which would come to be known as the double slit experiment, exposed quantum mysteries like no other. If you're looking for a description of reality based on certainty, your expectations would be shattered. We can get a pretty good feel for the double slit experiment and how dramatically it alters our picture of reality by carrying out a similar experiment, not on the scale of tiny particles, but on the scale of more ordinary objects, like those you'd find here in a bowling alley. But first, I need to make a couple of adjustments to the lane. You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back. And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit.
The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller.
You can picture them like this. Let's see what happens if I throw a bunch of these balls. When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you'd think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing: waves. Waves do all kinds of interesting things, things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others, and sometimes they'd cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes and what's known as an interference pattern. So how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
Particles are particles, waves are waves. How can a particle be a wave?
Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave.
A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles. And rocks are not waves. Rocks are rocks. So a rock is an example of a particle, an ocean wave is an example of an ocean wave. And now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow an electron got smeared out, and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described.
Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave.
That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electron is. That's where the electron is most likely to be.
And that's just very strange, right? So the electron on its own seems to be a jumble of possibilities.
You're not allowed to ask, where is the electron right now? You are allowed to ask, if I look for the electron in this little particular part of space, what is the likelihood I will find it there?
All right, so that gives you a good taste of the weirdness. I let the video go a little bit longer to get into that probability section. We're going to be looking at that later on, but that's starting to give you a taste of one of the ways that people try to explain this weirdness, right? And then more links here to do with the actual experiments, I should say here, just stuttering here, but the actual electrons and particles, of course, doing this. Let's just do this one here.
From Canada's Perimeter Institute for Theoretical Physics.
48.
This is where I come in.
Sorry, get the 848 mark here. 48.
So maybe again the deflection plays?
Herman Battleline and his team at the University of Nebraska-Lincoln are performing the double-slit experiment with electrons. It's the latest in a series of similar experiments dating back to the 1960s.
One of our goals was to be as close to the original thought experiments as we could possibly be.
The scale of the experiment is incredibly small. Each slit is only 100 nanometers wide. That's 1,000 times narrower than a strand of hair.
It takes a lot of time to get things lined up, a lot of patience to get things to work properly.
The experiment takes place inside this metal tube with a super hot filament firing electrons at the slits. After passing through the double slit, electrons strike a detector screen, which produces these green dots.
At first glance, you would expect that for classical particles, you would just get the addition of the two distributions. If you actually do it, there's an enormous surprise in store for us.
Instead of the distribution we'd expect from classical particles, electrons produce an interference pattern.
Electrons making an interference pattern. How is that possible?
Maybe the electrons are bumping into each other and repelling.
But how would that create an interference pattern?
What if we fire the electrons at the screen one at a time?
Electrons? One at a time?
Like classical particles?
Yes, like we did with the tennis balls.
Then they should form the same distribution the tennis balls did.
Should they?
If you were thinking of that wave as being built up out of many electrons, then surely the wave is gone, and surely the interference pattern must disappear.
The signal of the electrons hitting the detector screen is transmitted to a computer. The left image shows the electrons striking the screen individually. The right image reveals a pattern that is built up over time. Incredibly, after a large number of electrons hit the detection screen one at a time, they still produce the same interference pattern. So individual electrons behave like particles in arriving at specific spots on the screen. They also seem to behave like waves in building up an interference pattern over time. This shows that electrons have a dual nature. Physicists call this nature the wave-particle duality.
It's always amazing that we can actually see something that is a quantum mechanical effect on a physical screen in our lab. It's very rewarding to be able to actually do that, and it's a lot of fun.
And really excited about the double slit and what we can do in addition to what we've done so far.
You can look at this and you start pondering, what is causing this?
Is causing it, right? That's what we're going through here. This one is very similar, it's just a different animation of it in that this link works. I'm pretty sure the old link was copyright forbidden or whatever, it was dead. So I found a new link for it, but I'm not going to show it during the lesson here because I don't want to get copyright infringements. But yeah, this one goes through the same kind of stuff if you want to see a recap of it in a different way. And yeah, so we're seeing there must be a connection between particles and waves, right? Waves of what, right? Like, what are we talking about here? So the interference phenomenon found by Davison and Germer made the wave-like nature of electrons tangibly evident. But waves of what? One early suggestion made by Schrödinger was that the waves were smeared out electrons, as it showed in the video. This captured the feeling of an electron wave, but it was too rough. Like, what is it? When you smear something out, part of it's here and part of it's there. However, no one ever encounters half of an electron. Or a third of an electron or anything. Like the smallest amount of charge you ever find is that 1.602 times 10 to the negative 19, right? So it makes it hard to grasp what a smeared out electron actually is, or accept that it even is a thing, of course, right? As an alternative, Max Born sharply refined Schrödinger's interpretation of an electron wave, and it's his interpretation amplified by Bohr and his colleagues that is still with us today. Born's suggestion is that one of the strangest features of quantum theory, but is supported nonetheless by an enormous amount of experimental data. He inserted that an electron wave must be interpreted from the standpoint of probability. Places where the magnitude, a bit more correct to square the magnitude. When you do these calculations later in university, if you go on, you'll be squaring the wave equation to find out the probability of the electron being in a certain spot. So if the wave is large, or where the probability is large, right, the electrons are more likely to be found in places where the magnitude is small, or places where it's less likely to be found. So this is a peculiar idea. What business does probability have in the formulation of fundamental physics? We are accustomed to probability showing up in horse races and coin tosses and at the roulette table and so on, but that just reflects our incomplete knowledge. If we knew, this is the most probable spot to find an electron, the second most probable spot, and so on, right? It says, though, if we knew precisely the speed of the roulette wheel and the weight and the hardness of the marble and so on, the location and speed of the marble when it drops into the wheel, the exact specifications, of the material constituting the cubicles and so on. If we made use of sufficiently powerful computers to carry out calculations, we would, of course, according to classical physics, be able to predict with certainty where the marble would settle if we had enough information. Gambling casinos rely on your inability to ascertain all this information and do all the necessary calculations prior to placing your bet. But we see the probability encountered at a roulette table does not reflect anything particularly fundamental about how the world works. It's just information you don't have, right? Quantum mechanics, on the contrary, injects the concept of probability into the universe at a far deeper level. According to Born and more than half a century of subsequent experiments that are all found to work perfectly, the wave nature of matter implies that matter itself must be described fundamentally in a probabilistic manner. For macroscopic objects like a coffee cup or a roulette wheel, de Broglie's rule shows that the wave-like character is virtually unnoticeable, and for most ordinary purposes, the associated quantum mechanical probability can be completely ignored. But at a microscopic level, we learn that the best we can ever do is say an electron has a particular probability of being found at any given location. The probabilistic interpretation has the virtue that if an electron wave does what other waves can do, for instance, slam into some obstacle and develop all sorts of distinct ripples, it does not mean that the electron itself is shattered into pieces, but rather it means that there are now a number of locations where the electron might be found with a non-negligible probability. In practice, this means that if a particular experiment involving an electron is repeated over and over again in an absolutely identical manner, the answer for, say, the measured position of an electron will not be found over and over again. The same answer won't be found. Rather, the subsequent repeats of an experiment will yield a variety of results with the property that the number of times the electron is found at any given location is governed by the shape of the electron's probability wave. If the probability wave, or more precisely the square of it, is twice as large at location A than B, then the theory would predict that after subsequent many repeats of the experiment, the electron will be found at location A twice as often as location B. Exact outcomes of experiments cannot be predicted. The best we can do is predict the probability that any given outcome may occur. Even so, as long as we can determine mathematically the precise form of the probability waves, their probabilistic predictions can be tested by repeating a given experiment numerous times, thereby experimentally measuring the likelihood of getting one particular result or another. Just a few months after de Broglie's suggestion, Schrödinger took the decisive step toward this end by determining an equation that governs the shape and the evolution of the probability waves, or as they came to be known, wave functions. It was not long before Schrödinger's equation and the probabilistic interpretation were being used to make wonderfully accurate predictions. By 1927, therefore, classical innocence had been lost. Gone were the days of a clockwork universe whose individual constituents were set in motion at some moment in the past and immediately fulfilled their inescapable, uniquely determined destiny. According to quantum mechanics, the universe evolves according to a rigorous and precise mathematical formalism, but this framework determines only the probability that a particular future will happen, not which future actually ensues. Many find this conclusion troubling or even downright unacceptable. Einstein was one. In one of physics' most time-honored utterances, Einstein admonished the quantum stalwarts and saying that God does not play dice with the universe. And then Bohr's response was, "Stop telling God what to do." He felt that probability was turning up in fundamental physics because of a subtle version of the reason it turns up at the roulette table, some basic incompleteness or understanding the universe and so on. Einstein's view had no room for the future, whose precise form involves the element of chance. Physics should predict how the universe evolves, but not merely the likelihood that any particular evolution might occur. But experiment after experiment, some of the most convincing ones being carried out after Einstein's death, convincingly confirmed that Einstein was just flat out wrong on that. As the British theoretical physicist Stephen Hawking has said on this point, Einstein was confused, not the quantum theory. Nevertheless, the debate about what quantum mechanics really means continues unabated. Everyone agrees on how to use the equations of quantum theory to make accurate predictions, but there is no consensus on what it really means to have probability waves, nor on how a particle chooses which of its many possible futures to follow, nor even on whether it really does choose or instead splits off like a branching tributary to live out all possible futures in an ever-expanding arena of parallel universes. That's the many universes interpretation. We'll talk more about it later. These interpretational issues are worthy of a book-length discussion in their own right, and in fact, there are many excellent books that espouse one or the other way of thinking about quantum theory. But what appears certain is that no matter how you interpret quantum mechanics, it undeniably shows that the universe is founded on principles that, from the standpoint of our everyday today experiences, are bizarre. The meta lesson of both relativity and quantum mechanics is that when we deeply probe relativity, we'll see soon, but when we deeply probe the fundamental workings of the universe, we may come upon aspects that are vastly different from our expectations. The boldness of asking deep questions may require unforeseen flexibility if we are to accept the answers. So just a little bit of concreteness to this. De Broglie's idea was E equals mc squared, right? So the equivalence between mass and energy. De Broglie said, well, energy is h bar f, and so this, a connection was found between energy and matter, right? So, and waves for that matter. So this predicted that matter would have wave properties, and we used, and ended up being this wavelength equals h bar over momentum equation that we'd already seen, right? So in summary, the wave property of all matter is quantified by this equation, right? Which led to Schrodinger's wave equations. These calculate the probability of a particle being at any given spot. So most probably to be found here, or the three-dimensional picture that we saw earlier is kind of nicer. This helps us picture how a single electron or photon can interact with both slits. It really has a probability of being at both slits. But of course, isn't it really at one slit or another? Yeah, so let's go to that section. Oh, actually, I think we already watched up to a certain point. So I'm going to continue to 2150. Just writing that down for myself here, and we'll continue on.
I mean, that bugs anyone, anytime.
As weird as it sounds, this new way of describing how particles like electrons move is actually right. When I throw a single electron,
I can never predict where it will land. But if I use Schrodinger's equation to find the electron's probability wave, I can predict with great certainty that if I throw enough electrons, then say 33.1% would end up here, 7.9% would end up there, and so on.
These kinds of predictions have been confirmed again and again by experiments. And so the equations of quantum mechanics turn out to be amazingly accurate and precise. So long as you can accept that it's all about probability.
If you think that probability means you're reduced to guessing, the casinos of Las Vegas are ready to prove you wrong.
Try your hand at any one of these games of chance, and you can see the power of probability. Let's say I place a $20 bet on number 29 here at the roulette table. The house doesn't know whether I'll win on this spin, or the next, or the next.
1.
But it does know the probability that I'll win. In this game, it's 1 in 38.
21. 29.
So even though I may win now and then, in the long run, the house always takes in more than it loses.
The point is, the house doesn't have to know the outcome of any single card game, roll of the dice, or spin of the roulette wheel. casinos can still be confident that over the course of thousands of spins, deals, and rolls, they will win. And they can predict with exquisite accuracy exactly how often. According to quantum mechanics, the world itself is a game of chance much like this. All the matter in the universe
People, of course, find that kind of troubling or unacceptable. But yeah, so the implication on particles, though, is that everyday particles, or if everyday particles like tennis balls behave this way, as small quantum particles do, that'd be pretty weird, right? So each time you'd look at a tennis ball, it would just happen to be in a different spot, one of those spots that it has a chance of being. And so there are, if there were three possible locations, you have to be able to predict the chance of, you just predict the chance of where it would be. Later on, I'll be talking about quantum tunneling, and electrons are seen to do this. You have an electron in an area, and it physically can't get to the other side because the potential, there's too much energy. It can't appear in this other location, but it does. It's called quantum mechanical tunneling because there's a non-zero chance of it being over there without having crossed that barrier. It could have just, without the barrier there, it just has a chance of being in X number of different locations. So it's like if you had a rock next to a glass window, right? A window. And so if it had quantum mechanical probability chances of being in other spots, the rock could appear on the other side of the window. So literally you throw a rock at a window and it just goes right through, appears on the other side. It just happens to. So that is the quantum world. Clearly rocks don't do that because the de Broglie wavelength is so small and so on. But the real world actually is that at a fundamental level, which is really strange. So back to, one sec here. Right, I was contemplating showing a video that I saw recently about sort of how they developed Schrodinger's equation for the probability, but I think I'm going to save it for a future lesson because we're long enough here for this one. But yeah, so some idea questions to do with wave-particle duality for you. And yeah, that's all for now. Thanks for watching.